Welcome to the Python Programming Tutorial Series for Climate Mathematics Theory and Applications. Chapter 9, Python Graphics for Climate Science. In this video, we will plot wind velocity fields on a map, use ggplots, and create an animation using the Python language. Let's begin with figure 9.13. First, we're going to go in and prepare some variables. We're going to prepare a lat variable that is made from the NP line space between 75 and 5 with 6 digits in between, and we are going to repeat those 6 digits 12 times, and that in itself will be our latitude variable. Our longitude variable is made in a very similar fashion. We are going to create a NP line space from negative 165 to 165 with 12 numbers in between, and we are going to repeat those 12 numbers 6 times to create our longitude variable. Next, going into the wind vector variables, which will dictate the magnitude and movement of our wind vectors. Starting with the U vector, we are going to repeat the -1, 1, -1, -1, 1, -1 array 864 times. For our V vector, we are going to create it in a very similar fashion using a little different array, but we are still going to repeat the highlighted array 864 times. Now we are going to mesh together our latitude and longitude variables to get every single unique pair between those two arrays. We're going to name these unique meshed together arrays X and Y. Going into the setup of the figure, we're going to set up our figure using that PLT subplots function. We are going to create the projection used by that plate carré. We're going to add coastlines, and we are going to add state borders to our plot. Now we are going to go into plotting every wind vector in a for loop. Using this for loop, we're going to enter our longitude variable, then enter our latitude variable, and we are going to plot every single longitude latitude pair with a dot that is black. Now we're going to go into the quiver plot, which will be the arrows and the main item on our wind velocity field. We are going to use the quiver function on parameters x, followed by y, followed by our direction vectors, which are u and v. We're scaling them to 65, and these colors are going to be blue. We're going to add some labels and text to our plot as well. We are going to add a polar high in this longitude-latitude range. We are going to add a subtropical high text, a intertropical convergence zone text, and a subtropical high text. We're going to go ahead and modify the default axes, and our new axes are going to span from -180 to 180 and from -90 to 90. We're going to set those X ticks to the highlighted line, and we are going to set our Y ticks to the highlighted line. Now we need to format our lat and long so we do get appropriate axis labels. We're going to use a longitude formatter with a degree symbol equal to a blank string, and we are using a dateline direction label. We're going to do a very similar thing for our lat formatter using the latitude formatter function and setting that degree symbol to that empty string. We're also going to go in and set our major formatters on each of these axes to the variables we just created. Wrapping that entire block with a PLT show, we do get the wind velocity field on a map to pop up. We can see that we have polar high as our title. We have a subtropical high, an intertropical convergence zone, and a subtropical high. All of the blue arrows you see were created from the quiver plot function that we used on our X and Y and U and V variables. We do have a dateline direction label, which is going to be the 75 north through the 75 south, as well as the 165 west through 135 east. Moving on, we are going to go ahead and open a netcdf file. We are going to name it NCD using the NC dataset function. We're going to go ahead and go into this file. We're going to read some of their variables as well and name them appropriately for hopes to plot in the future. We're going to have a U10 variable dictated by the U matrix in that file, a V10 variable dictated by the V matrix in that file, and a lat and long variable. Figure 9.14 is the NOAA sea wind field for January 1st, 1995. If you wanted to see a similar example, it can be found at the following URL. Don't forget to close your netcdf files at the end of your code. Moving on to section 9.4, we are going to create a ggplot using data. First, we are setting up a dictionary of state names. We have the abbreviation being the index and the actual state name being the value in these dictionaries. We are going to create a state abbreviation array only holding the abbreviations of the 50 states. Next, we are going to create a data frame named stateDF. Using that pandas data frame function, we are going to have a column header named state where we are listing the state name values, which is going to go into that state names dictionary and only grab the values from it. The abbreviation column will hold the state name keys. We're going to go into that state names dictionary and only grab the key values. Next, going into figure 9.15, we need to create a figure using the chloropleth function. We are going to be plotting that state data frame that we created above. We do need a locations variable, and our locations are going to be dictated by the abbreviation column in our data frame. Our colors that we're going to set up are dictated by the different states, and we have location mode dictated by the variable US states. This is a built-in variable, just allowing Python to know that we need a US state map, and that is what we are plotting on. You can go ahead and choose a continuous or a discrete scale. We're going to go ahead and choose the rainbow continuous scale for our plot. We should update the layout of our interactive plot. We are going to update this layout and we are going to add a title text to it, as well as a scope of the USA. We're going to wrap that block in a fig show, and we do get this interactive color map of the 48 lower United States. We could go ahead and hover over any of the states, And we are going to get out the state name as well as the abbreviation. We can zoom in on this ggplot, and it allows us to look at these states that may have not have been seen before. Our colors are not unique in this plot. However, we do have a legend over here that you can scroll through to ensure that you are looking at the correct state with the correct color. This ggplot is very versatile. We can zoom out, we could zoom in, we can grab all of our state names and our state abbreviations. Moving on to section 9.5, entering our animation. There is a little caveat with this animation. It is slightly different from figure 9.16, but it involves all of the same components as the example presented in the book. First, we're going to go ahead and set up some variables that we will be using. The width variable, the height variable, and the size variable. These three variables correspond with the window that our animation will pop up in. We are going to go ahead and create an animation canvas, which we are going to use the TK function, which is found in the import list at the beginning of chapter 9. We're going to set this TK empty function to the variable TK. Next, we're going to set up our canvas that is going to actually create the animation. We're going to use a canvas function on our TK variable with the specified width, height, and color. We're going to go ahead and use the pack function on this canvas variable we just created. We are also going to set our color to medium violet red. Now we are going into the creation of the class named ball. We are going to be animating a ball, so we need to set up this class in order to animate the characteristics of the ball in our animation. Set up our class variable. We are going to define the self as this self shape using that create oval function. We are going to set a speed X and a speed Y and a self activate. That means once we actually activate this class ball, it will continuously go through the ball animation. We are also going to set up a ball update, and this will be running on itself. We're going to use the move function on the self shape and the self speed X by the self speed Y variables created in the definition above. We're going to set pose, which represents the position of our ball, equal to the canvas dot chords of our self dot shape. Then going into this for loop, which will just dictate that when our ball hits the edge of our frame, it is going to reverse directions and start bouncing in the other way. Now we are going to go ahead and create a function in which the ball will be an immediate on a particular cycle. We're going to name a global variable named switcher, and switcher is going to be set equal to true. We're going to define this function cycle with our global variable. We're going to use the tag raise with the BG input. If our switcher is true, then we are going to update that ball using the function we created above. If switcher is not true, we are still going to update our ball, but we are going to have a tag raise of ball 2. We can finally wrap this function with a tk.updateIdleTasks, which will allow each ball update to consecutively follow the last one. We're going to reset switcher equal to not switcher, which will negate our switcher variable. And then last thing in this function will be tk after 40 on our cycle. This will end our animation after 40 of our cycles. Going in to the actual animation itself, which will be similar to figure 9.16. This BG function we are creating creates a rectangle in which our animation will be in. We are going to use position 0, 0 as our starting position, width plus 1 as our width of our rectangle, height plus 1 as our height of our rectangle. We are going to fill it with a lavender blush color, and it will have the tag BG. Next, we need to create the ball instance using our ball function. This will just take the parameter that we are naming our ball, which is namely ball. Now we are going to animate our ball using the ball underscore update function. And we are also going to create a second instance of a ball. The next highlighted line creates the cycle at which the ball is going to be animated at. And then wrapping all of this in a tk.main loop will compile and show the animation. One thing in Python that we do need to realize is that when we run this block of code, this inline 16, you will get a new window to show up that will have the animation itself. I will now show you the animation that this code creates. After running that block of code that was previously shown, you do get this window to pop up. We can see that it's named tk as it was in the functions we created, and we do have a lavender blush background with a medium violet red ball bouncing in between our frame. This concludes part 3 of chapter 9, Python Graphics for Climate Science. Join us next time for chapter 10, Advanced Python Analysis and Plotting.